It is my pleasure to introduce Dr. Kevin Koestler. And I really hope this topic will be of high interest to you and actually very helpful in your research endeavors, because I find that, I found that few times Devin and his team saved us the misery of doing too many experiments that will still not tell us anything. We won't be able to discern null hypothesis, support hypothesis, or reject it. So I encourage you to, at some point, reach out to Devin. Devin is a professor and associate director of research operations in the Department of Biostatistics at the University of Kansas Medical Center in Kansas City, Kansas. He wears many hats, actually, all of them around the mathematical, statistical analysis. He's a co-director of the Biostatistics and Informatics Shared Resource at KUMC, director for Data Science Core School of Medicine at KU Cancer Center, and I know him from Kansas Institute for Precision Medicine, where he directs the quantitative omics core, one of the essential parts of the Kansas Institute of Precision Medicine. So I can talk about the research interests, but I think I'll let Devin actually introduce the very research he's interested in, and he will tell you how he actually envisioned navigating this webinar. Thank you.
Thanks. Can you hear me through this? I think I can probably set it. Is this a mic, a traveling mic? Okay, perfect. Wow, that was a great invite. Thank you. I really appreciate the opportunity to be here today. Before I get started, just a few things. One, at any point, if you got a question, feel free to interrupt me. This is less of a research talk and more of like a kind of a tutorial how-to. Okay, so interrupt me at any point. Before I get going, just to kind of gauge the audience a little bit, who here has taken a class in statistics? At least one class in statistics. Okay, all right, probably about half. Who here? Yes, those on Zoom, if you want to put it in the chat, you can. If you've taken a statistics class, that would be great. Who here has heard of like the concept of effect size, power, sample size? Okay, most people. Awesome. All right. Today, the goal is to kind of demystify some of these things. Now, we have to manage expectations, right? It would be impossible for me to deliver this so clearly that you walk away and you're ready to hit the ground running doing these calculations yourself. But I do think it's a realistic goal to at least get you to understand conceptually what we mean when we talk about effect size, power, and sample size, and how these three things interrelate with one another. Before we get into that, because I want to make sure that you all feel approachable, that I'm approachable, I wanted to start this out a little bit differently, right? I'm going to talk a little bit about my background and kind of how I got to be where I am right now at the University of Kansas Medical Center in the Department of Biostatistics and Data Science. So this is my roots. I grew up in Western New York near Buffalo. And in case you haven't heard, Buffalo is known for getting lots and lots of snow. It is also the home of the chicken wing. And anyone from Buffalo, they don't call it a buffalo wing, they call it a chicken wing. And it's also home to Niagara Falls. And of course, my beloved Buffalo Bills. The only thing that is harder than giving a talk on sample size, power, and effect size on a Tuesday at 3 o'clock in the afternoon is being a fan of the Buffalo Bills in Chiefs country. So I grew up in Buffalo and I went to Rochester Institute of Technology for my undergrad. And I started there in engineering and very quickly realized that I was not cut out for engineering. But I really enjoyed my math classes. So it was my second year, I declared math as my major. And RIT is kind of an interesting place. It's actually not in Rochester, New York. It used to be, but it was relocated in the 1960s into a suburb of Rochester called South Henrietta. And they had debated whether or not they should change the name, but the trustees weren't super enthusiastic about the acronym that would result if they went with the South Henrietta Institute of Technology. So they just kept it as RIT, Rochester Institute of Technology. So I studied math there. RIT is known for a couple things. It's a tech school. It's also known for the huge number of bricks that are on this campus, and they're the exact same brick. And in fact, there's a brick named after RIT because literally the entire campus is the same brick. In fact, they're in the Guinness Book of World Record for the largest amount of singular brick within like some square footage, within like a square mile. They're also known for their co-op programs. That was my first kind of exposure into the application of like statistics and math to solve problems in biomedicine. So during my junior year, I worked in a company that was in downtown Rochester called Ensign Research. Basically, what this company did was they predicted how certain drugs would metabolize based on chemical descriptors. So we're in the Department of Chemistry, right? Chemistry building, right? So all these things, all these chemical descriptors, how many hydrogen atoms, double bonds, single bonds, can we predict how that drug will metabolize? That was kind of my first exposure into statistics. And I really enjoyed it. And so I decided to pursue a graduate degree in statistics. And that took me to Brown University, which is in Providence, Rhode Island. So I headed east to the coast. And Brown's a great place, absolutely stunningly beautiful campus, especially this time of year. If you ever get a chance to go to Providence, go there in the fall, go to Brown. It's beautiful. A couple notable alumni. Emma was actually a student there when I was there, and I did see her a couple times, which totally makes you starstruck. You're like, oh my gosh, there's Emma Thompson. John Krasinski, who's in the office, I think graduated like a year before I started there. And then Ted Turner, he was way before my time. He's the co-founder of CNN. So my work in graduate school dealt with developing unsupervised clustering methods for high-dimensional omic data. And I hadn't had biology since high school. And I knew that in order to advance in that area, I needed a little bit more training in the biological sciences. So I did a postdoc. And so I headed north up to Dartmouth College, which is right on the border of Vermont and New Hampshire. Another very beautiful place this time of year. So there I was involved in a postdoctoral program called the Quantitative Biomedical Sciences. And so the philosophy of that program is if you go in, say, with a degree in statistics, you're going to cross-train in bioinformatics and molecular epidemiology. So that was where I cross-trained. And that gave me a lot more competence and confidence, I would say, with the biological underpinnings of the statistical work that I was doing. Then I made my way out west to the University of Kansas Medical Center. And that's where I've been ever since. The main area of work that I do is in developing and applying statistical methods for high-dimensional omic data. Most of the work is in the area of epigenetics. So a lot of my collaborations are in the cancer realm, looking at biomarkers for disease risk and for prognosis. But as Maggie mentioned, there are a whole host of other hats that I wear at the medical center. I'm the Associate Director of Research Operations in the Department of Biostatistics and Data Science. And then I direct or co-direct a handful of different cores that serve various research centers at the University of Kansas Medical Center. There's a common thread. Across all of those different roles, the common thread is that I'm either helping to deliver statistical support to people that come and want to consult with us, or I'm helping to facilitate that. Okay, so that's what kind of brings us here today. A lot of what I do in providing that type of support is helping people design their study. And a critical aspect of designing a study is how many samples do I need? This is like my life. This happens at least once a month where I'm on my way to go get a bagel or something in the morning or to go get my Mediterranean lunch in the cafeteria at KU Med. And someone stops me in the hall and they ask me if 3 mice is enough for their study. It could be. It depends. I can't give you an answer right now. I need to go get my bagel, but let's set up a call and let's chat about it. If I'm not confronted with that question, I'm very frequently confronted with this one. Can I just use a t-test? Maybe. It depends. So a statistician is good at what they do if they never answer a question in certainties, right? It's always like, well, it depends. And I guess that's kind of fitting because statistics is the science of uncertainty. So it would make sense that we would answer questions in an uncertain manner. So here are the goals. right? They're two fairly simple goals that I have today. One, as I mentioned before, to kind of equip you all with a conceptual understanding of statistical power, sample size, and effect size, and how all of these interrelate with one another. So we're going to talk about what they are. We're going to talk about how they're interrelated, and we're going to talk basically, okay, in very general terms, how do we calculate them? The second goal that I have, and this could be an entire full-length semester course, by the way. So I'm going to try to give you what could be a full-length course in like 15 minutes to give you some practical guidance on what type of tests you should use in certain types of situations. I'm going to keep this very, very broad, very general. We're going to talk a little bit about what we mean by a parametric and a non-parametric test, how to know which one is appropriate in a given context, and what are the implications if you misselect the test that you do based on the nature of your data. All right, so before we jump into our conversation on sample size, there are a few examples that I want to discuss to substantiate why this is so important. Okay, so these are two fairly recent examples. One is from a Bay Area tech company called Elkos. They developed a compound called AK006, which is a humanized monoclonal antibody for treating chronic hives. And they conducted a clinical trial, which we all know is like the gold standard for assessing a medical device, an intervention, or some new drug or therapeutic. And they enrolled 34 patients into their study, and it was a two-arm randomized controlled trial. So one was the active drug, the AK006, and the other was a placebo. The study went on for several weeks, and at the end of the study, when all the data was collected, it was found that there was no statistically significant difference in the active drug as compared to the placebo. And as a consequence of that, because it failed, this clinical trial failed, tons of people at this company were laid off. They lost a ton of their market share. A lot of people were laid off because the drug didn't prove successful over a placebo. Now, it may very well have been the case that the drug is not significantly more effective than the placebo, but the study only enrolled 34 people. That is not a very large sample size. And if you consider that that was split into two different groups, it's very likely that this study was underpowered. So people lost their jobs, the company lost a lot of money, probably because this study was underpowered for detecting a clinically significant effect. Another example, which is also apt and timely, is remdesivir for COVID-19. And this was a drug that was evaluated in a clinical trial, and this clinical trial was very well done. They had their sample size calculations on point. It was a double-blind, placebo-controlled, multi-center randomized trial. The problem with this one wasn't that their sample size calculation was correct. It was that their enrollment of participants into the trial, their accrual was too slow and it became too costly, and they had to shut the trial down because it was just becoming too costly. It wasn't accruing as fast as they had anticipated. In any case, no significant effect was found, probably because the study was underpowered. They had to close it down early. So this is a really big deal. And statisticians have recognized this for a long time. Okay, we've written papers about how important sample size is in the context of clinical trials and also basic and translational studies, which I think is probably reminiscent of a lot of the work that you're doing here. This is a basic flow diagram of how clinical research works, but basic and translational science isn't really that much different. Maybe there are a few less steps because in clinical research, we're working with humans, so there's more regulatory things we have to go through as opposed to like a model organism that we're experimenting on in a lab. But the important point here is that whether you're doing basic and translational science or you're doing clinical research, every study starts with a question, right? What is the study objective? What is the scientific question or questions that you want to try to address? So getting the question right and framing it in a detailed manner is really, really important, especially when you're working with a statistician who's trying to help you determine how many samples you need. It's critically important that that question be written in a very detailed way. Let's see this example here. Is drug A better than drug B? What does better mean? Drug A at what dose? Drug B at what dose? For how long? Who's the study population? How long are we going to follow these people? This is a very vague, non-specific question. But I'll tell you what, this is where a lot of it starts. When I meet or consult with faculty, a lot of times they come, they say, hey, I have this new drug that I think is going to lead to better outcomes in patients with triple negative breast cancer. And part of my job as a statistician is help to tease out the details. So what do you mean by better? How long is this drug going to be administered? How are we going to evaluate this? Let's see another example of this. This is a more specific way of asking the question. In population W, is drug A at a daily dose of X more efficacious in improving Z by an amount R over a period time T than drug B at a daily dose of Y? Now, I recognize that that's a bit of a mouthful to get through, but there's a lot of things in this statement that are really, really critical, especially as it pertains to estimating how many samples you need to conduct that study with adequate power. Asking the right question means defining what difference we care about. Where is that in this statement? Improving Z by an amount R. Okay? R is like the effect size. We'll come back and formally define that in a little bit, but just keep that in the back of your mind. That tells us the difference in the outcome Z between the two different groups. In fact, people have thought long and hard about this and have developed a framework to help us write scientific questions. So there's this framework called PCOT or PCOT, not exactly sure how it's pronounced, PICOT. And this was published in 2010 by Rios et al. And this helps us think and conceptualize what belongs in the statement of a question. So P stands for population. Who are the patients, or what is the population of interest? I is what is the primary intervention being considered? Okay, what's the active drug? What's the active intervention or medical device? C is like the control, placebo. What's the alternative to the active drug or the intervention? O is the outcome. What relevant clinical or biological outcomes are we talking about? And what difference between the groups do we care about? And then T, what is the time frame to observe the outcome? So if we look back at the question, the specific question that we had before, we can start to dissect what is what in this statement. So P in population W, I, the intervention group, those getting drug A at a daily dose of X, C, the comparator group or control group, those getting drug B at a daily dose of Y, O, the outcome that's improving Z by an amount R, and T, the time frame over a period of time T. All right, let's put it to practice. I'm going to give you 15 seconds to read this, and then we're going to do thumbs up, thumbs down, thumbs in the middle. What do we think about this statement? Where's the Jeopardy music when you need it? Okay, can I have a volunteer to read it?
Favor. Yeah. And then it's 25 years, but the 6-week high intensity. 6-week high intensity interval training program consisting of 45-minute sessions 4 times per week, compared with a steady state cardiovascular training program of equivalent duration and weekly frequency, results in greater improvements in cardiorespiratory fitness over 6-week study duration.
Okay, so notwithstanding the fact that this is a really long sentence, it is a complete sentence. But what do we think about this? Thumbs up, thumbs down, thumbs in the middle. Ready? On 3. 1, 2, 3. All right. Hold on, keep them up. We got a lot of thumbs up. We got 1 thumbs down, 1 in the middle, another thumbs down, 1 in the middle. Okay, so we've got 2 people with thumbs down, 2 people with thumbs in the middle. So I want to focus on you guys. Why? What's missing, according to you?
I don't know that's the value that's associated with the difference.
Okay. The value associated with the difference, the effect.
Effect, yes.
All right, very good. You were listening. Effect size. Yes. So this is pretty darn good. Okay, this gets a lot of those points. Does it have the population? Yes. Men age 18 to 25. Does it have the intervention group? Yes. It's an interval training program consisting of 45-minute sessions 4 times a week. Does it have the comparator group? Yes. Cardiovascular training program of equivalent duration and frequency. Does it have the O? Cardiorespiratory fitness. But what's lacking is how much of a difference. And more specifically, what is cardiorespiratory fitness? How is that even measured? All right, so it's the O that's the problem here. T, the duration, 6 weeks. We got that. So what if we did this? Result in greater improvements in cardiorespiratory fitness, comma, as defined as an increase in VO2 max at the end of a 6-week study duration. It's better. Well, but I don't know how much of an increase, right? I've now specified what I mean by cardiorespiratory fitness and how that's going to be measured. That's VO2 max. But I've not specified the amount of a difference that I'm looking for between my 2 different intervention groups. Now I have it. Defined as a 10% or greater increase in VO2 max over the 6-week study duration.
How do you define, I mean, based on what do you find 10% being significant?
That is the $1 million question, Maggie. And that's not one that a statistician can answer. That's hard. And that's where when we work with people, when we work with collaborators, it's a dance, it's a tango. Like there's some stuff that I can do as a statistician. I can take it pretty far, but there's some stuff that I need from you as the content area expert. What do you think you could defend? Like if we take this study, for instance, would the people that study and read this literature of different types of fitness programs be convinced that a 10% increase in VO2 max after 6 weeks is significant? Those are the people we're trying to convince. Well, and we're trying to impact patients' lives and help them improve. But that's not something that I come up with as the statistician. Now, I can tell you what effect size you can detect with 80% power and a fixed sample size. I could tell you that with these things fixed, you're powered to detect a 10% or greater difference in VO2 max between the 2 groups. But I can't come up with that for you. Does that make sense? Okay. Any questions on this? Okay. So why does this matter? Well, when we write down questions like this using the Peacock criteria, it really focuses us to consider what is meant by a successful intervention. We also need to be mindful that our trial or study or experiment, it needs numbers, not just ideas. At some point, we need to say, I'm going to do 5 mice. I'm going to enroll 10 people, right? We need to have the rubber meets the road. Now, the number of units, whether they be people, mice, clinics, whatever, that you need to address your question is intimately tied with a difference that you deem relevant, a 10% increase in VO2 max. Okay? I'm going to hope to show you how over the next few slides. That brings us to the big 3. All right? The big 3 are effect size. That is like R in the way we define the Peacock criteria. It's the difference that you want to be able to detect. What is clinically or biologically significant? Sample size, how many participants, units, or individuals do we require for your study? And then power is the ability to detect an effect if it truly exists. If there truly is an effect in your data, it's our ability or the probability of actually saying that it exists. Now, to put these concepts into practice, we're going to consider another fairly simple example. The objective of this study is we want to compare the mean value of some biomarker, let's say prostate-specific antigen, and we want to compare that between white and black men that are at high risk for prostate cancer. Okay, so that's the objective of the study. Now, there's going to be a little math, but I promise it's not going to get too crazy. These are just Greek symbols. That's all they are. Let's walk through them. So here's our notation. Mu sub W and sigma sub W respectively represent the mean PSA for white men and the standard deviation for white men. Similarly, mu sub B and sigma sub B represent the population mean and standard deviation of the biomarker PSA for Black men. Okay, pretty simple. Now, if we're going to address this objective, a sensible thing to do is we're going to enroll a bunch of people, white men, Black men at high risk for prostate cancer, and we're going to measure the biomarker, the PSA, and we want to compare it. So we're going to get N sub W white men, we're going to get N sub B Black men, and then we're going to test a hypothesis. Our null hypothesis is that the PSA, the mean PSA, is the same. It's the same exact between white men and Black men. The alternative is that it's not. It's different between white men and Black men. Now, we can say those in words, but we can also write them mathematically. Based on the notation that we introduced, the null hypothesis, as I just stated it, is equivalent to testing whether mu sub W is equal to mu sub B. Okay? The alternative is that mu sub W is not equal to mu sub B. I can also write this a little bit differently in terms of this parameter delta. Don't freak out. It's another parameter, it's another Greek letter, but all delta is the absolute difference in the two means, right? So I can restate those null and alternative hypotheses as saying the two means are the same is the same as saying that their difference is 0, right? And the alternative equivalently is saying that their difference is not 0. Okay, now, in order to understand power and sample size and effect size, we have to define what we mean by different types of errors. And that gets back to the way statistical inference is set up. When we collect data, we conduct a test and we make a decision on the basis of that test, right? You know, we get like a p-value, right? You've done it before, right? We reject or we fail to reject. Is it less than 0.05? We're making a decision. Now, consider this table. There are things that can happen when we make that decision. Hypothetically, there's some truth that exists out there in the universe. We don't have access to that truth, but there is truth. For the example that we considered, the truth is either that there is no difference in the PSA levels between Black men and white men, or there is a difference in PSA levels. Now, we make a decision on the basis of enrolling people into our study, collecting the data, and running a statistical test. If I say that there's not sufficient evidence of a difference in PSA, and the truth is that there really isn't, then I'm happy. I've made the right decision. Okay? Similarly, if I say the PSA levels are different based on my statistical test, and the truth is that they really are different, then I'm also happy. I've made the right decision. It's what happens in the off diagonals is when things get interesting. Alpha is what we call type 1 error. Okay? That's when we say there's a difference based on our test, but there truly isn't. So truly, the PSA level is the same between white men and Black men, but the result of my test is I said that there's a difference. I've made a mistake. That we call a type 1 error. The other type of error, conveniently, is called a type 2 error. That's saying that there's not a difference in PSA levels when there truly is. Now, where does power come into play? Power is just simply 1 minus beta. It's saying that there's a difference in PSA when there really is. Question.
I don't know if this is just the wording, but when I read and it says no sufficient evidence of a difference in PSA versus when you say PSA levels are different, does that mean there's not enough evidence, but it could be?
So here's where things get very nuanced. When we test a null hypothesis, if you think back to the previous slide, look at how I have it written. Null, mu W is equal to mu B. Alternative, mu W not equal to mu B. If I collect data and I test that null hypothesis, let's say my p-value is bigger than my pre-specified type 1 error rate. Let's say our pre-specified type 1 error is 5%. My p-value is 0.3. What am I going to do? No, we'll fail to reject. Failing to reject the null does not mean that the null is true. Just because I fail to reject the null because my p-value is bigger than 0.05 does not mean that the two means are the same. What it means is that there's not sufficient evidence in the data to say that they're different. It's a semantic thing. Failing to reject the null does not imply that the two means are the same. It just says that there's not enough evidence to say that they're different.
Okay, that's fair, how we word it.
So
But
that's
when
how-
you have less than 5%, it means that it is.
So if our p-value was
Yeah.
less than 0.05,
Yeah.
so
That's PSA level are different, right?
so if the truth is that the PSA levels are different between white men and black men, now we never observe this truth. This is like a universal thing that we never observe. If the truth is that there is, and the result of my test is a p-value less than 0.05, my decision would be I'm going to reject the null and conclude that the PSA levels are different. And I'm going to be happy. I made the right decision. That's the second smiley face. Does that answer? This is one of those things that you just need like time to digest on your own terms. Because I think a lot of these concepts are based on the way we've been trained. They don't immediately just float off the tip of the tongue. But hopefully this helps demystify things a little bit. Okay? The important point here is that there's the truth and there's the decision. And there's what happens when we make mistakes. And there's two types of mistakes, a type 1 error and a type 2 error. And power is just 1 minus the type 2 error. It's the probability or saying that there's a difference in the difference in PSA levels when there truly is. So more generally, if we think about this in terms of like H0 and H1, we have a decision, right? We either fail to reject the null or we reject the null. If the truth is really the null, that the two means are the same, and we fail to reject the null, we're happy we've made the right decision. Similarly, if we reject the null, when in fact the truth is the alternative, that the PSA levels are different, then we're happy we've made the right decision. And then of course we have our two different types of error, our type 1 error and our type 2 error. So when we think about it like this, power, formally speaking, is the probability of correctly rejecting the null. It's the probability of rejecting the null when we really should. There really is a difference in PSA levels. What's the probability that I reject the null and say that there is? Okay, you know what's an intriguing thing is that the way statistical inference is set up is very similar to what happens in a courtroom, right? We're all kind of familiar with courtroom in the United States judicial system. A defendant is presumed innocent until proven guilty, right? So the null hypothesis is the presumption of innocence. The alternative hypothesis would be proof of guilt. Now, what happens throughout the course of a trial is you have witness testimony, you have evidence that's presented. That's like data, right? To us, right? That's data. Then you have a jury that's hearing this testimony, that's seeing this evidence. That's like a statistical model. They're taking in that data, that testimony, that evidence, and they're going to make a decision. But the ultimate decision rests with the judge who makes the final verdict. That's the decision, reject or fail to reject the null hypothesis. So all of this plays out in a courtroom. It's just that in statistics, we formalized it with mathematics. All right, a couple housekeeping items so far before we press forward. Type 1 error is rejecting the null hypothesis when we shouldn't. Type 2 error is failing to reject the null when we should. Power is the probability of correctly rejecting the null. N is a parameter we use to denote sample size. It's the number of units, participants, individuals in our study. Delta is what we call our effect size. That's the difference of PSA levels between the white men and the black men. Or it could be like odds ratio or hazard ratio, depending on what our endpoint is. And then sigma is what we call uncertainty. It's the variation, say, in the PSA levels that we've measured on our white men and our black men. Okay? Now, how do all these things fit together? Now, I'm being very, very general, but all of these parameters have a relationship. So if I fix the effect size I want to detect, 10% difference in VO2 max, I fix the uncertainty associated with the endpoint, VO2 max, and I fix my type 1 error, When my sample size goes up, as I get more people in my study, my power goes up. All right, so I have better power with more people with those things fixed. Similarly, if I now swap out delta and n, if I fix my sample size, sigma and alpha, as my delta goes up, my power goes up. So I have better power for detecting bigger differences. That's going to make a lot of sense after this next example. Keep that one in the back of your mind. I'm going to give you an example in like 2 seconds that I think is going to make that one really clear. Also, if I fix the sample size and the effect size, if my uncertainty or my variation in the endpoint that I'm measuring and comparing between my groups, if that goes up, my power goes down. Okay? Let's consider an example. All right, this is silly, okay, but I think it will help. Consider 2 different situations. We got 2 cups, okay? One of them is 50 degrees and one of them is 51 degrees Fahrenheit. So the delta or the effect size is 1 degree. There's a 1 degree difference between these 2 cups. Now imagine that we put our finger into the 2 cups and I ask you the question, which one's warmer? Well, that's going to be kind of hard, right? Only a 1 degree difference. It's going to be really hard to detect. Some people might be sensitive enough to do it, but it's going to be pretty tough. And if I did that with 20 people, probably like a little more than half might get it, right? But pretty close to half would get it wrong, right? Because that's such a subtle difference. So if I did it with 20 people, let's say 9 got it wrong. I'm sorry, 9 got it wrong and 11 got it right. So the number of correct would be 11. So the proportion of correct is 11 divided by 20. Okay, the number of people that got it correct over the total number of people, that's 0.55. Now let's say I increase the temperature a little bit in cup 2. Now I go to 53 degrees. Now the delta is 3. Now what do we expect is going to happen? Do we think more people are going to get correct? Yes, right? This is kind of like the effect size idea. As the effect size increases, our power is going to go up. So now 13 out of 20 get it. So the total number of correct is 13. The proportion of correct is 13 over 20, or 0.65. Now you can see how this plays out. As I increase the difference in the temperature between these 2 cups of water, the proportion of people getting it correct goes up and up until eventually you reach a point where that difference in temperature is just so vast, unless you have some underlying medical condition, you're going to tell the difference, right? And in fact, we can be really creative. I don't know why that like squiggly thing there, but just look at the blue line. We could actually plot this out, right? The proportion of correct on the y-axis with the temperature difference, i.e. my effect size, on the x-axis. And a lot of times in statistics, we power a study at 80%. What we see here is our power is increasing as a function of increasing effect size. Not surprising. 80% is our typical standard, just like a 5% type 1 error rate has become just a tradition, a standard. So we have 80% power. So I'm just looking at where that blue line intersects my horizontal dotted line. And what that tells me is I've got 80% power to detect the difference of 9 degrees or more between the 2 cups of water. Now, this is a really silly example, but this is exactly what plays out when like we write code to actually do this. We've got computers. We don't have to sit in our offices with cups of water. We can code this up. Now, I know that this might look scary. The math is coming back, but we're going to walk through this because we're going to demystify, and I'm going to help you to understand and appreciate that this really isn't that much more complicated than what we're doing with the water. It's just we're writing some code to do it for us. So the first step, if we go back to our PSA example, is we need to randomly generate data under the alternative when delta is not equal to 0. So I need to say what delta is. That's where I rely on my collaborators to help me. What is a clinically or biologically relevant difference? Then what I do is I'm going to generate data for a certain number of white men, N sub W, a certain number of black men, N sub B, and I'm going to generate the data randomly such that the difference in the PSA levels is that delta that I'm pre-specifying. Based on the data that are randomly generated, I'm going to conduct my statistical test. The test is going to result in a p-value. I'm going to compare that p-value to the type 1 error rate that I set, which typically is 5%. If it's less than 5%, I'm going to reject the null. If it's greater, I'm going to fail to reject the null. And I'm going to record my decision. Then what I'm going to do is I'm going to repeat this. Because I'm writing up computer code, I'm going to repeat this like 1,000 times, 10,000 times. My power, if you remember, is the probability of correctly rejecting the null. That's just going to be the number of times that I correctly rejected. I set delta to be non-zero. I generated data such that there is a difference in PSA levels between the white men and the black men. I can actually calculate this empirically. What is the fraction of times that I correctly reject the null hypothesis out of the data that I simulated? So let's unpack these one by one. The first one, randomly generate data. Let's focus on the white men first. So here is some simple R code, right? Nothing crazy here. The first thing that I do is set my parameters. I need to say how many men I have. So I'm just going to say that there are 20 men. And then I need to specify what the mean PSA levels are and their standard deviation for these men. And I just got that from a paper, right? It's a little bit dated from 1996, but if I was going to do this for real, I'd try to get like a more updated publication. But that's where those numbers came from. Then I'm just drawing data from a normal distribution with that mean and that standard deviation. And then I can look at a histogram of the data that I just generated, and it looks like that. Now, this probably doesn't look like the typical bell shape that we're used to seeing for a normal distribution, but you also have to keep in mind that there's only 20 samples, okay? So if I had upped this sample size, it would look more bell-shaped or more normal. Now, I can do the same thing for black men. I'm going to specify how many men I want to generate data for. I'm going to specify delta, or the difference in the PSA levels. And I'm going to say that their standard deviation of PSA is exactly the same as white men. I'm going to generate from a normal distribution, and I can look at the histogram. Cool? Now, I can take those two histograms, and independently, it's kind of hard to see, like, well, I've generated the data so that the black men have a slightly higher PSA than white men, but it's a little bit easier to see if I do it in the context of a box plot, right? Now I can see that there is a slight, black men have slightly higher PSA based on the way that I've simulated the data. And in fact, the difference of the central tendencies is delta. That's exactly the difference that I specified. That makes perfect sense. So remember, as part of the simulation procedure, we've specified what delta, what that difference is. So now I've done that. I've generated my data. Now I need to conduct my statistical test. So I take the two data that I generated and I do, let's say, a t-test, right? Simple two-sample t-test. And here's the result of the test. Here's my output. P-value is 0.75. Well, that means I failed to reject, right? Okay, so I record that decision. I failed to reject. Now I'm going to repeat that 1,000 times. And I'm not going to show you 1,000 times. Let's see if we can get this out of the way. Oh no. Okay, here we go. So there was the test that I just did, the first one, p-value of 0.75. I failed to reject. So in my little table, reject H0? Nope. There's my second iteration of new randomly generated data. My p-value is 0.04. Reject? Yeah. And then all the way down to my thousandths output, p-value 0.86, fail to reject. Okay, so I have all these yeses and nos. Did I reject? Did I fail to reject? Now I'm ready to compute the power. What is the power? The power is just the number of y's divided by the total number of iterations, which is 1,000. That gets me, in this case, 93 over 1,000 yeses. So my power is 0.093. Not very good. Okay, not very high power. So I can visualize that in the form of a plot similar to what I did with my cup, temperature difference. So that's where delta I preset to 0.2 in this particular simulation, but I can also preset delta to be 0.4, 0.6, 0.8, 1. And in fact, I can look at that smooth relationship of how power changes is a function of increasing effect size on the x-axis. Here, I fix my sample size to 20 per group, And what we can see is that right at about an effect size of 1, I almost am reaching 80% power. Almost reaching 80% power with this sample size of 20. Well, guess what happens if I increase the sample size? If I now try 50, well, I'm powered to detect differences that are even smaller, 0.6. I don't have to, right? With 20 samples per group, I'm only powered to detect differences of like 1 or higher. But if I up my sample size to 50, I'm powered to detect differences of 0.6 or higher. If I even further up my sample size to 100, I'm powered to detect differences, whoopsie, of 0.5 or higher, right? So if we were to interpret this with a sample size of 100, we have 80% power to detect differences of 0.5 nanograms per microliter or larger in the mean PSA level between white and black men. Now I can give my collaborators something that they can chew on and ask, like, is it practical to get 100 in each group? I don't know. That's for them to decide. I'm going to pause here for a second. Any questions on this? Does this kind of make sense? Clear as mud, right? All right. Any questions on Zoom?
Um, Hi, Devin. I have a quick question. So all these statistical tests are only for normal distributions. I'm correct, right?
So I'm generating the data from the normal distribution. You're correct. And I'm conducting a test. And we'll get to this in a little bit. I am conducting a t-test, which assumes that the data are normally distributed. So I'm stacking the deck a little bit in my favor. So we'll get to this in a few slides where what are the implications if I have selected my test wrong, if my data really aren't normal? Or what happens if my data are normal, but I do a test that doesn't require normality? What are the consequences of that? So right now, I've assumed that my data come from a normal distribution, and I'm conducting a test that assumes normality.
Thank you.
See, here's the thing that's really tricky. In advance of doing this study, we don't know, right? I've not run the study yet or collected the data. How in that world do I know that it's normal? You're kind of taking a shot in the dark. And that's why these power and sample size analyses are not perfect. They're estimates, they're approximations. But just because they aren't perfect doesn't mean they're not useful. All right?
Can I follow up on that?
Yes.
So is the data showing non-normal distribution because you don't have enough samples collected? Or is it really that there is a scenario that it's non-Gaussian?
That's where it's really, really hard. So in this scenario, the histograms that I showed you didn't look like normal. But I showed you the code. I definitely generated them from a normal distribution. So don't always be misled by a histogram that doesn't look normal. A lot of times we can learn about what's been done in the literature. If there is a similar biomarker, some other pilot study that's been run that had a slightly bigger sample size that it looked approximately normal, well then, even though my histogram might not look that way, I at least have another study to say, hey, they did a much larger study and it looked approximately normal. I'm going to assume normality here. But that's what makes this really tricky, is that a priori we don't know, right? So now, this is a lot of the times like when I'm working with someone. So we're going to kind of put this to practice. So framing the question, and this gets back to our whole like PCOT, how do we frame a question? So studies have shown that Black men tend to have higher PSA levels on average than white men, even after controlling for confounders or potential other sources of variation. So in the literature, it has been noted that a difference of approximately 0.5 to 1 nanograms per microliter of PSA by race may be clinically relevant. So there are the sources for that. So now I can specify my research question. Among adult men living in the US, age 40 to 49, at high risk for prostate cancer, there's my population. Black men, there's my intervention group, have a mean PSA level that is 1.0 nanograms per microliter larger, there's my outcome, than white men, there's my control group, as assessed during their annual wellness checkup, there's my time. And I can do that calculation and I can determine how many samples do I need to detect that clinically relevant difference. So I'm looking to see where my power curve intersects with 80%, and it's right there. I would need 22 men per group to conduct this study with 80% power at a type 1 error rate of 5%. Right? Okay. So the last thing that I'm going to say on power, effect size, sample size before I switch gears for what will only be probably about 10 more minutes. Do not confuse statistical and clinical significance. If I give you a big enough sample size, everything's statistically significant. So even in this situation here where we have two histograms, okay, two distributions that are essentially on top of one another. I mean, come on, let's face it. There's not really a difference there, right? The mean of one group is 67 and the mean of the other group is 67.1. But at a large enough sample size, if I have 8,000 samples per group, my power is 80%. I'm rejecting the null hypothesis 80% of the time to say that there's a significant difference between those two groups. So do not confuse clinically significant with statistically significant, right? All right, a couple parting pieces of wisdom as it pertains to the first part of this. Collaborate early with statisticians, bring them into your conversations early and often. Start with the question, what effect size do I care about? What's clinically or biologically significant? And then finally, you don't need to know the math. Of course, I don't want to discourage you from learning the math if you're really interested in it, but having an understanding of how these three things interrelate with one another and what happens if I move this one up or this one down, I think is really important. And I think you will be able to have a better dialogue with your statistician, understanding the interrelationship between these three different factors. Okay. Before I switch gears, any questions on power, sample size, effect size? So any questions here?
To clarify, when you wrote this, the code, that's an RStudio that you were using? Or are we?
Yes, that was
okay?
an RStudio. Yep.
So we can have those practical maybe at the end.
Yeah.
Are there maybe other software that's easier than RStudio? Or okay, we'll talk about this later.
So, here's what I would say. This kind of goes back to my final point. Like, it depends how far you want to take it. Like some people, R is a wonderful resource in that it provides so much flexibility to do so many different types of things. When it comes to power and sample size analysis, the complexity of it is a function of how complex the model is that you plan to fit to analyze your data. There are closed form solutions. So Pavor, you use G-power. So for some of the power calculations you did, like a t-test or a z-test, there are closed form formulas. You don't need to go through the simulations like I did. There's actually a formula for computing sample size. But as you get more complex models, like say you've got a time to event endpoint and you're fitting a Cox proportional hazards model, or you're doing a Kaplan-Meier survival analysis, the more complex the model, you're not going to have a simple formula. And so R provides a lot of flexibility to do this simulation type of approach. And you can do this with any model. It's very easy to generate data. And so it's extraordinarily powerful to know how to do that. But that's where like a statistician would come into play. Like if you're just doing this here and there, using something like PASS or G-power, or what's the other one, Kazi? G-power, PASS, there's another one. nQuery is another one where you just go in and point and click your way. But remember, you got to have the intuition to know how these things relate. So if you're getting something wonky, you know, like, whoa, wait, something's not right here. You see what I mean? Okay. Okay, this one should go relatively quickly. Providing practical guidance on what tests to use in certain types of scenarios. Again, you could have an entire full-length semester's course on this. All right, so this is like literally the tiniest of appetizers in this area. So let's frame the context. Assume that we have a continuous variable that we want to compare between two groups. Very similar to the PSA example that we've discussed with white men and black men. Okay, first and foremost, okay, before we even talk about parametric, non-parametric, blah, 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 first and foremost, the test that you do should address your research goal, right? If your goal is, I want to compare the PSA levels between white men and black men, or I want to compare the mean PSA level between white men and black men, then your test should do that. It should compare the mean between the two groups. If it doesn't do that, then it doesn't matter whether it's parametric or non-parametric. It doesn't even address your research goal and should be thrown out. Second, it should honor the nature of the data. Is your data continuous? Is it categorical? Is it binary? Is it time to event? Do you have repeat measures data? Whatever method or test you come up with should honor the nature of your data. And then third, it should accommodate important features of your study design. So in the study of black men, white men, PSA levels, that would be conducted as an observational study, right? There's probably things about white men and black men that could confound the association that I want to adjust for in my models, like socio-demographic background. Where do people live? I mean, we could sit here and speculate. There's probably a great many things that we'd want to control for that are sources of variation that we'd want to put in our model. That should be another consideration in terms of what test or model we use. So with that said, in this example in mind, I did promise you parametric and non-parametric. It's actually pretty simple. Parametric is when we assume a distribution for our data, right? Common examples of parametric tests. You've all heard about it, t-test. We assume the data is normal or approximately normal, all right? But t-tests can come in different flavors, by the way, all right? There are t-tests where we assume equal variances of whatever it is we're comparing between the two groups. We assume that it has the same variance. So that would be akin to saying that the variation of PSA levels is the same in black men and white men. That may or may not be reasonable. There's a variation of the t-test called the Welch's t-test that allows for unequal variance. There's also linear regression or ANCOVA. These are really valuable if you want to control for covariates or confounders. Like in our study of PSA, you might want to control for socio-demographic background, where do people live, age, those types of things. They assume normality as well. There's also an entire paradigm of statistical testing called Bayesian methods, right? I'm not going to get into that, but they also assume a distribution for your data. Non-parametric is distribution free. We don't assume normality or any distribution for that matter. Wilcoxon rank sum is a very popular non-parametric method. Kolmogorov-Smirnov, that's used to compare distributions, okay? Resampling-based methods. Now, I know what you're thinking. Why don't you always just use distribution free? Does anyone know the answer to that? It seems like distribution free is the go-to, right? You never have to assume a distribution. Why not just always err on the side of caution and go with that? Well, the reason is if your data really do come from a distribution, and by the way, a lot of things are normally distributed. And at a certain point, the central limit theorem kicks in. So if I have a sufficiently large sample size, guess what? The central limit theorem tells me that the sample mean is going to be approximately normal. And so, and many things in nature do follow a normal distribution. And if your data really do, the parametric methods are going to be more powerful. We can see that right here. So I'm going to consider that example that we looked at before, the PSA levels between white and black men. And we're going to consider 3 different approaches: the 2 sample t-tests, which is parametric, and then 2 variations of non-parametric tests, Wilcoxon and the Kolmogorov-Smirnov. Remember, here I am generating my data from a normal distribution. So I'm stacking the deck a little bit in favor of the t-test. But when it turns out that the data really are normal, the t-test provides the best power. Wilcoxon isn't far behind, but the t-test is superior in terms of power. Kolmogorov-Smirnov comes in 3rd place. Now, this is when I have 20 samples per group. If I go to 100 per group, well then, whatever advantage the t-test had over the Wilcoxon kind of dissolves. Now, there's not really a huge advantage of the t-test compared to the Wilcoxon rank sum. I can do whatever, and I basically get equivalent results. What happens if I take the sample size down? Well, when we see the benefits of t-test is when the data really are normal and the sample size is small. So when the sample size is small, but your data really are normally distributed, t-test gives you the best bang for your buck. But Wilcoxon, again, isn't too far behind. What happens to the t-test, though, when I simulate data that's not normal? So I can generate data from what's called a t-distribution, which is kind of, it looks like a normal, it's symmetric, but it has heavier tails. So it's a type of distribution where you have a lot of outliers. That's what we mean by heavier tails. So if I do a t-test in a scenario where I only have 20 samples per group, when the data really aren't from a normal distribution, but this heavier tailed t-distribution, the Wilcoxon does better than the t-test. All right, and this is just an example of a t-distribution. T-distribution converges to a normal when the degrees of freedom goes to infinity. The example that I used was really low degrees of freedom, so very heavy tails. So in this situation, Wilcoxon outperforms. I know this is confusing, right? So where does this leave us? What test do we do? So these are some general rules of thumb. Use a t-test when the data are approximately normal. Your sample size are modest to large, that is bigger than 20 per group. And if you care about comparing means, right? Because the null hypothesis that we're testing in a t-test is that the two means are the same. You could use a Wilcoxon rank sum when the data are skewed, heavy-tailed outliers, or otherwise non-normal, and the sample sizes are small, less than 20 per group. The Wilcoxon tends to be more reliable than a t-test when n is very small and the data are non-normal. So only use the t-test when the data are small if you feel very confidently that that marker that you're comparing is normal.
For me, for any clinical, the clinical data I collect, because I know I cannot let enough data points to demonstrate that it's normal. That's why I always go for the Wilcoxon.
Better to err on the side of caution.
For analytical measurements, purely analytical method, right?
Yeah.
I would always go, please, I can go to t-test and make this assumption that, yeah, it's normal.
And guess what? Sometimes we do both. And there's value in seeing whether two similar types of tests, whether they're confirmatory, whether they provide different results, and we can learn something when they differ and when they're similar. There's something to be learned there. So practical advice and wrap up. Selecting the appropriate method or test for your data is really more of an art than it is a science. It requires practice and experience, trying different things, seeing how they respond. You should have a plan when you're doing an experiment. You should know in advance, this is what I'm planning to do in terms of a test, but also an opt-out. If when you run the study, your data come back and they look very non-normal, or they have a lot of outliers, you should be willing to switch gears to a different test that is more accommodating of those features. And then finally, when in doubt, consult with a statistician. The earlier, the better. On that note, how do you get in touch with us? So this is, we're a pretty friendly group, right? I mean, at least we look friendly. We look happy in that picture, but we are. These are my colleagues in biostatistics and data science. We have several different research-intensive cores that support centers throughout KU Med, and also centers that span KU Lawrence and KU Med, like our KU Cancer Center. We have a biostatistics and informatics shared resource, quantitative omics core, data science core. So we've got the people and expertise to help you out. We have a website to get in touch with us, but you now know me. I'm sure can make my contact information available, and I can link you up or get you set up in a consult with one of our statisticians. Guys, that's all I have. Happy to take any questions.
Hi, Devin. Can I ask a question?
Yes, of course.
So let's say that we are doing a kind of biological study, and so we have limited amount of resources or something like that. So we cannot have a lot of samples. So in that case, let's say that the statistician says that, okay, you need at least 50 samples or 100 samples, but we have resources only to do 50. So what can we do at that time of a situation?
Yeah, that's a really great question. So there are sometimes situations that we're confronted with where practical or logistical constraints limit the number of samples that we could possibly do. In those types of situations, because this comes up all the time, what I like to do is to help the investigator understand what effects you would be powered to detect. And I also try to come up with ideas on how we can. So if you remember in the different things that impact power, uncertainty. So sigma, I had that denoted as sigma. As uncertainty goes up, power goes down. So are there things that we can do to limit or decrease the uncertainty in what it is that we're measuring and comparing without changing the sample size? Sometimes there are very clever things we can do with the experimental design that allow us to decrease that sigma, like taking a more homogeneous population. That typically will decrease sigma. There are also strategies called blocking that can help decrease the sigma. So sometimes if our sample size is fixed, there are other things that we can do in the experiment to help increase our power that don't have anything to do with collecting more samples. I also like to just give the investigator an idea of, with this number of samples, here are the effects that you're powered to detect. And can we kind of go back and forth together to understand, in your field, would that be clinically or biologically significant? Would that effect be relevant for people? So that's kind of where I'm at on that question. I don't know if that helps, but I guess the two parts of that, responding to that, is there are sometimes things that we can do experimentally to increase your power, even if your sample size is fixed. They have nothing to do with collecting more samples. And then second is just understanding what effects you are powered to detect with your constraints. Here's the total number of samples that I can do, what is financially possible, and here are the effects that I can detect. And sitting down and thinking and trying to understand whether or not those are clinically or biologically relevant.
Okay, thank you.
Mm-hmm.
And Baker's conundrum was a good.
Very similar. Yep. Yeah, we just recently went through this. Yeah, we kind of adapted our strategy, right? You initially came to us and you were seeking guidance on how many samples do I need, right? And we had come up with a strategy, and on the basis of what you were doing, we got wildly unbalanced sample sizes between the two groups, or between the three groups, right? And the revised strategy is now, okay, that would have been impractical to do. With the finances you have and the logistical constraints of the samples at your disposal, how many total samples could you feasibly do? Now let's fix that, and then let's ask the question, what effects am I powered to detect? And have those borne out or close to bore out in your pilot data. So sometimes we just manipulate the strategy a little bit.
Okay, thank you. And I just needed a minute to think through, but now think I have two questions. What you were saying before about ways to be clever with experimental design, I wanted to explore the idea of biological replicates and technical replicates. So in a very practical example that my group faces, we go to the biobank and there's a tube of plasma that's 2 milliliters, and that's all we're ever going to get because that's all that the patient donated. Is there value to conducting multiple replicate measurements, which I would consider like technical replicates, taking a tiny portion of that and analyzing it, and then another portion, but it's the same person's plasma? Does that convey value versus going to the bank and getting 2 mils of plasma from a different individual subject?
You're not going to like my answer.
No, that's okay. I have no horse in this race. I just want to know the answer.
I told you, like any good
It matters.
statistician.
It depends. It depends. It depends.
It depends. So what does it depend on? First and foremost, it depends on what you are trying to accomplish with those samples. If your goal, for instance, is let's say you're going to measure some biomarker and you've collected blood from a group of individuals. And some of the individuals have the disease and some of them do not have the disease. And let's say your goal is to determine whether or not there is a biomarker present in blood that distinguishes, that separates out the people that do and don't have the disease. In that type of situation, based on the way I frame the question, you want biological replicates. You want your samples where you're going to measure the biomarker to be from different people, right? Some number of people that have the disease, some number of people that don't have the disease. Now, sometimes we're interested in what's happening within an individual. Like, so technical replicates can be really valuable in a variety of different contexts. They can understand, for whatever device we're using to measure the biomarker, what does the variation look like? That helps us to understand the variation in that device, because we're literally measuring the same sample, the sample collected from the same person at the same time. We're measuring it using the same device. That helps us understand variation in the device. There's also a situation where technical replicates can be really useful for mitigating what's called batch effects. So batch effects come up a lot in microarray data. So I ran an array on 10 samples and I ran another array, and batch effects are technical variation that has nothing to do with biology, that come about different reagents, different times of day that they were run, different people that ran them. So if I ran a technical replicate of one person in this batch, and then again in this batch, any variation that I see in that individual is attributable entirely to batch effects, entirely to technical variation. And I can leverage that to learn how it differs so that I can make a correction for everything else that was different between this batch and that batch. Does that make sense? So there's value to both. Like, it depends on what you want to do.
And could I just ask one unrelated other question?
Yeah.
The thing that I am stuck on the most, I can understand the sample size and much of the PICO things that the framework, I like that a lot. I'm curious about where to look for effect size information. Do you have particular types of journals that tend to be the go-to sources to get clinically relevant effect size data? Because I feel like I wouldn't know where necessarily to look for that information.
For what we do, Rebecca, like, so if you're more in the clinical space and you're doing a lot with like clinical trials, that literature, I think, has a better anchor, is better anchored for finding clinically relevant effect sizes. You can go to other clinical trials that might not be exactly what you're proposing, but I think in that literature, things are a lot more well developed and the answers you can find, okay, in the literature. For what we do, which is more on the, I don't know, more the molecular biology end of the spectrum, it's really, really tough. Is a log fold change of 2 a biologically relevant difference in expression between the two groups? Maybe. I don't know. I wish I could point you to something. That's the thing that I struggle with all the time when I meet with my basic science and translational colleagues. So a lot of times it is really hard to define what's biologically relevant. So what I wind up doing is giving them, for a range of different sample sizes that they could be considering, here are the different effects that we're powered to detect. Are there any existing pilot studies on something similar? Are these effect sizes even in the realm of possibility from what we've done in our pilot experiments or what our collaborators have done in their pilot experiments? Are these effect sizes even in the realm of possibility? A lot of times it's like that because it is hard to find those in our space. Yeah. Anything?
Yeah. Other than she was just asking.
Well, any questions online? I think so. Well, I can hang around a little bit, but you guys have been great. Thank you. They were great questions. I really appreciate your time. Hopefully that was helpful.
No, that's great. I remember, I want to say 2018, you and your team, you guys did webinar on RStudio and how to. There was 18, 19, something like this. Do you do that from time to time? Those kind of tutorials online, webinars now?
For like our studio
Yes,
specifically?
I specifically remember attending one.
I don't know, but I can look into it for you.
Okay.
You know, this wasn't specifically the group that I oversee, but we kind of intersect with them. 2 weeks ago, they did a bioinformatics workshop where part of it was devoted to like R. But it was like a 2-day bioinformatic workshop. A little bit of R programming, how to process, quality control, align, and analyze RNA-seq data. But I can dig around a little bit.
Yeah.
I know people that teach our class and probably would have the materials to do a 2-day, 1-day.
Do you know if there are resources for scripts that you can actually find scripts and then just modify the? Are there any
Yes. So
secrets?
Coursera is really great. And you know what? I'll be honest with you. Like GPT tools are extraordinarily helpful. If you know the right question to ask. So here's the thing. If you don't know what to ask or you ask it inappropriately, you might not get the desired code that you want, right? So you're kind of learning with it. But that is essentially what we've been doing. Like how I learned R was just Googling. This was before GPT exists. That's what we would do. We'd go into Stack Overflow, we'd Google, hey, I'm trying to fit this model, I'm getting some weird results, like someone help. Inevitably, someone else had run into the same issue, and there you could find them through forums. But now, like, this is where GPT tools like that can be extraordinarily helpful. I'm serious. They can really improve your workflow. You can learn how to code, but you do have to know how to ask it the right questions. So knowing a little bit of R, if that's the direction you want to go, I think is really helpful. But let that be a resource to you.
Great, thank you. If I see no other questions, but Devin will be here for a few more minutes, so you can have a one-on-one chat. Thank you again. I know you had a busy schedule, so thank you for donating the time for us and for our patrons in the center. And this year we'll have one more webinar, December 9 on BPL, then beam pen lithography. So I'll keep you posted. Thank you all in the room and folks on the Zoom.